Greetings everyone, Professor Simon here again. Now it's time to talk about the Fundamental Theorem of Calculus for line integrals, sometimes called the Fundamental Theorem of line integrals. Okay, so here's where we kind of left off in the last lecture. We were talking about just line integrals over vector fields. Okay, so that's the most generic type of line integral. And the thing is, we also talked a couple of lectures ago about what a conservative field is. Okay, so it's that special kind of vector field such that the field itself can be rewritten as the gradient of some potential function. And of course, we're making the statement that the potential function needs to be continuous on the region in question. Okay, so being conservative really means that f is the gradient of some function, right? And the way we test for a field being conservative for a two-dimensional field, right? We just say that the y component, the second component, partial derivative with respect to x, is the same thing, has the same result as the first component, partial derivative with respect to y. If it's a 3D field, then this just generalizes to the curl of the field being 0. Okay, so the non-rotational, the irrotational kind, is also conservative here. Okay, so if this is true, then you should be able to find some potential function such that his gradient is your current vector field. Well, all right, cool. Apply this statement to a line integral, right? So the line integrals that we just got through talking about last lecture, f dot dr, which by the way is the same thing as f dot t ds, right? Don't forget, that's the same thing as this, f dot t ds, which means we're just dotting the vector field at each point on the curve that we're following with the tangent vector of the path itself, right? Over the length incremental. But this is the more appropriate way to talk about it, because really, what is r? R is when we parameterize the curve, right? So this curve is being described by whatever our r vector function is. So f dotted with the dr incremental really is the same thing as dotting with that tangent vector along every point. Okay? But r is a more direct connection to what we're really doing. Okay? So apply this. The vector field is the same thing as the gradient of the potential function, right? But the potential function is essentially a function of x, y, or x, y, and z, depending on your dimensional size here, right? This f is a function of your x's, y's, and z variables, right? So when I reparameterize the curve c to get dr, or just r so that I can get dr, I'm also reparameterizing the x, y, and z, or x and y, of the function, right here, right? So my function is actually going to be thought of as a composition of the parameterization with r. So that what that really does is it converts our potential function basically into a function of one variable, t, the parameterization variable. Okay? And dr here is the same thing as r prime dt, right? That's just another way of writing dr. Dr is really kind of like a shorthand here, right? And then don't forget, when we were doing line integrals, when we switch from the actual line integral of a curve into the world of t, the parameter t, right? It more or less becomes a definite integral at that point. Okay? So then right here, this is just the derivative of f with respect to r, because look, it's a chain rule. I can do derivative of f, leave the inside alone, times the derivative of the inside. That's a chain rule. So this chunk right here is just the same as doing the derivative of the function parameterized with r, right? Parameter t. But integral, derivative, dt's, right? Those are inverse operations the way these are arranged. So what I really get is the fundamental theorem of calculus, right? F of b minus f of a from Calc 1. This is now a definite integral, okay? And it works in the same fashion. So what I really got is the function from when t is b minus the function from when t is a, right? Because when I plug the upper t into my parameterization r, right, I get a point that's at one end of the curve. That's what this r of b stands for. It's the end point. And then r of a is the beginning point, right? So I'm just doing f of the end point minus f of the beginning point there. Well, let's sum it all up. FT4LI, that's fundamental theorem for line integrals, right? There we go. If I do a path integral, f dot dr, over a path c, okay? And it can be any path in this case, then the result is just f of the end point minus f of the beginning point of the curve c, okay? And there are many curves that go through, the two given points. And the only stipulation is that the gradient of this little f has to be the vector field capital F there, which, again, that implies that the f that you're starting with, the capital F there, has to be a conservative field, okay? So the fundamental theorem for line integrals works for conservative fields. It's basically what we're getting at here. Example. I have this vector field I've named E, and you've probably seen it a couple times already from a couple of different lectures past so far, right? Turns out this E is a conservative field, right? And I feel like we probably tested that before. It's conservative, I know, because I did the partial with x of the second element, right? And the partial with y of the first element. Both times I get negative 2x over y squared. So E is a conservative field. That then gives you the idea, hey, if it's conservative, then E must be the gradient of some vector function. So here's what I do. I set up the two partial derivatives of the potential function, not vector function, potential function, right? I set up these partial derivatives to be the two elements, right? If this is a gradient, then the partial x derivative of the potential function should be the first component. Partial y derivative of the f function should be the second component. That's how a gradient works. So I'm setting up these two differential equations here, and I'm just going to use the antiderivative on each one. And you'll notice both times, right, if I do an antiderivative with respect to x and an antiderivative with respect to y here, both times you get x squared over y. So the only thing that could be really extra in there is an added constant to be your potential function. However, just like in fundamental theorem in Calc 1, since I'm doing a subtraction between ending and beginning points, the constant really doesn't matter here because it's going to get subtracted away anyway. All right? So I'm not worried about that piece. I'm just going to use my potential function is x squared over y. So then the path integral, the line integral of E dot dr is going to be equal to this function evaluated at the ending point, 3, 4, minus f at the beginning point, 0, negative 5. Which, when I plug in the x's and y's here, I end up with 9 over 4. If you go back to my last lecture, we were talking about line integrals. I did this one a couple of different ways and with a couple of different paths. And you definitely want to make sure you notice that we got 9/4 both times. Okay? And the thing that I know you want to kick me for is, hey, why don't we just do this? Because this is much simpler, right? Well, we gotta build up to it, right? Got to build up. This is what we're building up to here. We're almost to the final result for this particular thing. Okay? So then there's some other verbiage here, some other terminology that goes along with this, okay? Considering that you've seen this before with two other paths, and now I'm showing you this without even using a path, and we're still getting 9/4 because E is conservative, then what we say is that if you're doing a line integral along a path inside of a conservative field, right, a conservative vector field, then the integral is called path independent, right? Obviously, it doesn't matter what path I choose. If f is conservative, right, then I didn't even have to choose a path or parameterization of r or anything. I just needed to know where does it end, where does it begin, and I just need to know the potential function, right? So line integrals in conservative vector fields are path independent, okay? So you've seen an example of path independence. Now let's look at an example of the opposite. And you've probably seen this vector field in my previous ones too. It's a good one to use here. This vector field, y over x comma negative x squared, and I want to integrate along a path that starts at the point 2, 3 and ends at the point 6, 1, right? In fact, we even did this particular integral a couple of different ways in the last lecture, okay? So on the side here, notice that if I take the second component and do the partial with x, I get negative 2x. And if I take the first component and do the partial with respect to y, I get 1 over x. Which means, since these two are not equal, then B is not a conservative vector field, right? Not conservative. So what does that imply? It implies that B cannot be written as the gradient of some vector function, some potential function, right? Okay, that's the way gradients work. If you have a gradient of something, then that field that you get will be conservative. Vice versa, the alternate would then, the contrapositive would be true. If I don't have a conservative field, then it can't be a gradient of some function right there. Not one that's continuous anyway, right? Okay, so then the line integral is going to end up being path dependent, right? It's going to matter which path I choose. So let's take a look at that. Let's do a couple of different pathways. First, let's do the pathway like we did in the last lecture, xy equals 6, right? It's a piece of a hyperbola that hits those 2 points in particular, 2, 3, and 6, 1. And then for curve number 2, the pathway that I'll choose is just a straight line, x plus 2y equals 8, which happens to be the line that directly connects those 2 points. Okay? So just like in the last lecture right here, I'm going to do this one in the differential mode. It was pretty straightforward that way. If x times y is equal to 6, then y is equal to 6 over x. So then this integral, and I'm just using the letters little a and little b to represent the points. It just saves me a little bit of writing. I'll have 6 over x, which is going to be 6 over x squared dx, minus x squared, but x is just 6 over y. So that's 36 over y squared dy. All right, so then I've just got some antiderivatives to do there. I'll be evaluating negative 6 over x plus 36 over y from the points A to B, right? But point A is the point 2, 3, and point B is the point 6, 1. So when I plug in B, I'll be plugging in 6 and 1, right? So that's going to give me negative 1 plus 36, minus, if I plug in A, I guess I'll go ahead and make this symmetric. If I plug in A, which is 2 and 3, so 2 here and 3 here, right? 6 over 2 is negative 3, and 36 over 3 is 12, like so. Okay, and then right here I have plus 3 and minus 12 basically. which is going to give me 26. Okay? So that should look familiar to you, right? We've done that one before. Let's do it again. Different path this time, right? So my y and x substitutions here are going to be different. Incidentally, even if I did this different path and had different substitutions on a conservative field, it wouldn't matter. They would add and subtract out to be the same thing. But since this is not conservative, you're going to see this gives me a different result. So y is equal to, well, let me write that down for you here, just so we can keep track of it. Obviously, x is equal to 8 minus 2y. Y would then be equal to 4 minus 1/2 x. Okay. So then my integral from a to b, y over x is going to be 4 minus 1/2 x over x dx minus x squared. So that's 8 minus 2y squared dy. Okay. If I simplify this right here, I will have the integral from a to b of 4 over x minus 1/2 dx. And then right here, all I'm going to do is factor out something from each piece. That's going to give me minus 4 times 4 minus y squared dy. And I just noticed that I can do this because it's just going to make the antiderivative easier to find by just doing a quick substitution there. Okay, so let's see. Right here, I'm going to get 4 times ln x minus 1/2 x. And then right here, if you'll notice, what I can do is a quick u substitution where I'm going to let u equal 4 minus y, right? Which, of course, du is then negative dy, right, for right here. So it's going to absorb this negative, and all I'm really going to have to do then at that point is integrate this with a power rule, right? Okay, so then that's going to give me plus 4 over 3 times 4 minus y to the third power. And then we're still evaluating this from a to b, well, of those 2 points, right? So let's substitute that in. At point B, x is 6 and y is 1. So that's going to give me 4 ln of 6 minus 3, 1/2 times 6, plus 4/3 times 4 minus 1 is 3 cubed is 27, right? Okay, now when I plug in a, that's 2, 3, I'm going to have minus 4 ln 2 plus, because of the double negative, 2 over 1, so plus 1, and then minus 4/3. 4 minus 3, right, is 1, cubed is 1, times 4/3 is 4/3. Okay, so here's the numbers. That doesn't look like it's going to add up to 26, does it? It doesn't. Here's what I can do, though. I can simplify this 4/3 of 27 into 36, right? This piece right here is 36. Which is 9 times 4, right? Then I've got minus 3 plus 1 is negative 2. Plus 36 is 34. Minus 4/3, right? So I've got 34 minus 4/3. So that's 33 minus 1/3. So 32 and 2/3, right? Which is 64 plus 2, 66 thirds. Right? double check me now. No, 90. Ooh, I almost messed up on that one, didn't I? I sure did. Let's go through it again. 36, right? Minus 2 is 34. Minus 4/3. I took 1 out of each, so that's 33 minus 1/3, which is 32 2/3, right? So 96 plus 2, 98/3. There we go. Okay, and then right here, notice I've got 4 ln 6 minus 4 ln 2. That's just going to give me 4 ln of 6 divided by 2, right? 3. You could also, I guess, write that as ln of 81 if you wanted to, but really it's not, going to get much better, right? The point is, it's not 26, okay? So this particular integral is path dependent, and it's because the vector field that the paths are going through is not a conservative field, okay? Here's another example of path independence, but it's in 3D now, right? I have a 3-dimensional vector field, and what I want you to notice is that the mathematics acts the same. Even though it's in higher dimension, we can still treat it the same way. The major difference is going to be, how do I know if this vector field is conservative or not? I can't just do a couple little partial derivatives now. I'm going to have to use the curl. All right, so let's start with that. The curl of f is going to be equal to the determinant, right? I, j, and k, of partial with x, partial with y, partial with z, and then my pieces of my vector field. Z squared plus 2xy, x squared, and 2xz, right? Okay, so let's do the determinant here. Equals, and then let's get this vector thing going. If I do the I column here, I'm going to have the y partial derivative of 2xz. There's no y's in there, so that's 0, minus the z derivative of x squared, also, so minus 0. Right, looking good so far. Got some zeros. The j column here, right, I'll have the x derivative of 2xz. That's 2z minus, negative and plus, right? Because it's alternated. Okay, so then I've got the z derivative of z squared 2xy. There's no z in that part, so it's just the z squared. So plus 2z. Also looking good, right? That's going to zero out. And then the k column here. So I've got the x derivative of x squared, right? 2x. Minus the y derivative of z squared 2xy. No x, no y there, so it's just going to be the 2x here. So what we're getting is the 0 vector, right? There's the 0 vector. What does that mean? F is a conservative field. Right? So then we can continue. It's going to be path independent. I don't need to pick a path now, right? So f is conservative, then further implies that means I've got a potential function out there, some continuous function whose gradient is equal to this. Well, then we've got to figure that out. Okay, so next that means f is the gradient of some f. So that means the partial of f with respect to x would have to be equal to my first component over here, z squared plus 2xy. So this piece of information is telling me that f is equal to xz squared plus x squared y plus some other potentially some other function of y and z. Okay. Partial of f with respect to y would have to be equal to my second component, x squared, which is telling me that f would have to be equal to x squared y. Look familiar, right? Plus some other function of x and z. And then lastly, my z partial derivative of f would have to be equal to the third component, 2xz, which is telling me that f would have to be xz squared, look familiar, plus some other function of x and y. Okay, well, if I compare these, I'm noticing the way they line up, right? This is the same in both places, and this is the same in both places, right? So these two pieces don't actually have anything to contribute to this guy right here, okay? So then that's telling me that my potential function, right, if I bring all of this together, my potential function of x, y, z would have to be equal to xz squared plus x squared y plus some other constant, right? But remember, in this case, I'm not worried about the constant because it's going to get subtracted away. Okay? So then my line integral over some path C, I didn't pick a path, don't need to, right? It's conservative, so it's path independent, of f dot dr. Again, r would have to be picked, a parameterization of the curve, the pathway. I don't need it in this case. I can simply say it's just the potential function f of a, which is 2, 1, 3. Ouch, I'm messing up already. I meant f of b minus f of point b minus f of a. So that's 4, negative 1, 0 minus f of a, 2, 1, 3. And I've got my potential function over there ready to roll. Okay, so then this is equal to, right here I've got x times z squared, right? So 4 times 0 plus x squared y. So 4 squared times y minus 2 times 3 squared. And then again, minus because of the negative, right? X squared, so that's 2 squared times y, which is 1. So I have 0, minus 16, minus 18, and minus 4 for a grand total of negative 38. Right? Okay. So again, path independence. Doesn't matter that I went up to three-dimensional path, right? I'm going through 3 space there. As long as you can show that the vector field is conservative, that means I can get a potential function, and then the integral is simply undoing the derivative in that case, right? I'm just using the fundamental theorem for line integrals. All right, I just wanted to take a second to give you a better visual of that integral that we just did with that 3D vector field that was conservative. Here's a visual of that vector field, and I've got it pretty dense. Let's lighten it up just for a second so that you can see sort of the direction. They do seem kind of random, but then if you pay attention to some of the groupings, you can see some of the motion that they'd be moving towards. Let's shrink it a little bit here now. Let's see. No, that's too much. Okay, yeah, this is good. Here we go. So you can, if you move around it for a little bit, you can see the patterns that start to form in here. Like you see that the vector's turning this way and then pointing up and then going this way. But one thing you will notice is that you're never really going to get any total swirling of anything going on here, right? And you can see the lightweight right here in the center, and as it gets further out, right, almost in a radial sense, it sort of spreads out to larger vectors in the extremities there, right? You can see it right here. It's light in the center, and as it moves out, it diverges outward, if you will. Hence the meaning of the divergence that we usually measure. Okay, but the curl is 0. So the overall feel that you should get is that there's not going to be any actual full rotations going on here, even though there is a lot of swirling. Okay. Now, real quick, let's take a look without the vector field, a representation of the path that we're doing is basically the endpoints of this line, right? This line right here represents the straight path between those 2 points that we were talking about. 2, 1, 3 was the beginning one, and 4, negative 1, 0 being the other end of it, right? You can see the 2 endpoints there, right? Okay. Now the thing that should be boggling you is that this path is one possible path. And since this is a completely independent path, the integral itself was path independent, you get the same result from walking this path as you do, say, a crazy path that has trig programmed into it, something like this, right? If I had this crazy path going through the vector field, it has the same beginning point and the same ending point, right? Before negative 1, 0 is the ending point over there, as the straight path that's shown here, right? Same beginning and ending point. So as far as this vector field is concerned, when I integrate, the line path and this crazy looking path have the same value as far as like total work and other things that you may want to do a path integral for. So take a look at these things mixed with the vector field now, right? Let's first look at the line, right? The line moving through this vector field, you can see, has certain points where it's going to match the direction and other points where you're going to have only part of the vectors dotting and moving in the same direction, right? Because the tangent vector on this line is just going to go along the path of the line itself, right? Rather boring tangent vector, which, you know, sometimes is good to be a little boring there, but, right, you don't really need this advanced thing to visualize a straight line. On the other hand, if you want to take a crazy path, you know, something like this, take a look at the tangent vector on this one. It starts out pointing almost straight down towards the plane there. And then let's move it along here. Look at the way it goes. So all of these dot products that's happening between these two vectors as this thing flows in that direction, after adding up all these different dot products, they actually end up being exactly the same as if I had added them all up in a straight path. Just because this is a conservative vector field. So it spreads out in just the perfect way with just the perfect sizes at every point. such that any path adding up all of these dot products would end up with the same result. That should scream in your mind amazing, right? So let's continue talking about path independence in conservative vector fields. So like we were just saying, of course, path independence comes from integrating on a line integral in a path that's going through a conservative field. So one other thing that path independence can imply here is that all path integrals that are through a conservative vector field will equal 0 if that path is closed. Now let's be a little more specific about closed, okay? Closed means that a curve is going to meet back up to the same point that it started, right? It's going to go through some path and then come back to its point of origination. And we need to further stipulate that it needs to be around a simply connected region. What does that mean, simply connected? It means you don't have to do anything crazy to get from any one point to any other point, okay? For example, obviously, it's just some region that's all together and the curve just goes around it, right? Simply connected. If I'm breaking it into 3 different curves that I have to define parametrically different, that's fine, as long as the points all meet up and there's no separations in there. A couple of examples of not simply connected. If you've got a big old hole in your set, right? It's not going to be simply connected because I've got 2 different curves that are not connected to each other that you're technically path integrating over, right? You're trying to cut out a piece of it. Well, that curve is not connected to the other curve. Same thing here. If I've just got 2 separate regions, right? 2 different curves, C1 and C2 are separate here, right? It's not simply connected, okay? So here's why, okay? Imagine I've got point A and point B, and I'm going to integrate some pathway C1, and then I'm going to integrate back from B to A on pathway C2. So if I say that, big C is C1 plus C2, then I'm going around this way and then back around to A again. So that's a closed path, right? Simply connected region. And this is what happens. I can split the path integral into an integral on each pathway, right? Since f is conservative, it actually didn't matter which path I choose. For C1, starts at A, ends at B. So it's going to be the potential function at B minus the potential function at A, plus the C2 starts at B and ends at A. Again, f is path independent, so it really didn't matter. What matters is that it starts at B and ends at A, so that's f of A minus f of B. Complete reverse order, right? Because it started where the other one stopped and vice versa, right? So everything adds out. Because the vector field is conservative, therefore path independent, when I do the orientation, that's the key here, right? If I orient the curve one way and then do another pathway that's oriented exactly the opposite with the same endpoints, everything just gets zeroed out, okay? So if you have a completely closed path, right, you can split it up into however many pieces you want. If it's over a simply connected region, that path integral around the whole thing is going to be 0 in conservative fields, okay? Now, real quick, what happens then if it's not a conservative field? Let's look at that example, and then we'll do one on a conservative field also. Look, okay, so I'm going to integrate this field right here, y, negative x. Notice it's not conservative because I can do the x derivative of the second component, the y derivative of the first component, and they're not equal, right? So that's not a conservative field. And I'm going to take some curve and split it into 2 pieces. The first piece is going to be the line y equals x between 0, 0 and 1, 1. The second curve is going to be y equals x squared from 1, 1 back to 0, 0. Okay? So if this was conservative, the integral over the entirety of that path should come out to be 0. but this is not conservative. So then it should actually be non-zero, right? Unless you've got something real trivial like 0 plus 0, like if both pieces were 0. But that's like a small subset here. In general, right, since it's not conservative, I'm expecting non-zero results here. Okay, so here we go. On C1, this is going to be the integral over C1 of y dx minus x dy plus, same thing on the other one, right? Plus curve 2, y dx minus x dy. Doing my dot products here. But on curve 1, y and x are equal, right? So this piece right here is going to be the integral from 0, 0, I'll just write it out, to 1, 1. Y is equal to x. So I have x dx, right? X is equal to y. So I have minus y dy, right? Plus curve number 2 goes from 1, 1 to 0, 0, right? 1, 1 to 0, 0. And in that case, y is equal to x squared. So I'll have x squared dx minus x would then be equal to square root of y. And I can take the positive because notice we're just dealing in quadrant 1 here. Dy. All right. So some pretty straightforward pieces there. I'm going to have 1/2 times x squared minus y squared, right? And that's going to be going from 0, 0 to 1, 1. Okay? Plus, antiderivative now is going to be 1/3 x to the third minus, that's y to the 1/2. So then it goes up to y to the 3/2, right? Times 2/3. And that's from 1, 1 back to 0, 0 again. Okay? So when I plug in 0, 0 here, I get 0. When I plug in 1, 1, I get 1 squared minus 1 squared, I get 0. So this piece right here is just 1 minus 1 minus 0, right, which is 0. Plus, let's see, right here, I can factor out a 1/3 times. If I plug in 0, 0, it's all zeroed out. Minus, if I plug in 1s, right, that's just 1 cubed is 1. Minus, I factored out the 1/3, not the 2. So it would be minus 2. Right, if I'm plugging in 1 and 1 here. Just 1 to 3/2 is just 1. Okay? So this piece right here is 0. And then right here I'm getting negative, negative 1 times 1/3. Final answer, 1/3. Okay? So I did a completely closed curve, right? All of C went from one point, then back to the beginning point again. But the answer I got was non-zero, right? Again, F was not a conservative field, so I was expecting to get something like that. And this implies, should start giving you an idea of why we've named these fields conservative. Because remember, one of the applications of the line integral of f dot dr or f dot t ds was the work, energy required to move things, right? If I do work in conservative fields, then going to one point, then coming back doesn't, it requires energy to do one and then I get the energy back by doing the other basically. Or if I go in circular paths, I basically end up where I am as far as energy levels go. If I'm in a conservative field, my work integrals tend to be 0 on closed curves. Okay? If I have a pure electric field and I do some work to push two of the charged particles together in that field and then do some more to do something else to let it come back, right? Then totally whatever energy I spend pushing them together and then letting them come back, I get all the energy back. So essentially I did 0 work, I expelled 0 energy because I got it all back. But if you do something like that in a non-conservative field, then what happens? You go along one path and then you try to come back. And somewhere in there you've either gained or lost something. Typically in our world you end up losing something, right? A lot of things tend to burn off energy like friction and different forms of other heat loss things. So if you go along one path and then you try to come back, you've lost some energy somewhere, right? That's just one example, but this is a lot of the math behind that. If something's not conservative and you do it on a closed loop, you're still going to end up gaining or losing something. So let's take a look at this vector field too, just so I can show you a non-conservative one here as well. There's our two paths that we're interested in that were connected, right? And you can see the tangent vectors pointing in the direction of the first leg there. And that's the orientation we're going to be taking, up the straight line and then down the curved path here. Okay, but more importantly, let's take a look at the vector field and how you would think that that would interact with the path, right? So here, you can see the small vectors now, but watch as I increase the size, the portion of the vectors that you can actually see. It's not actually moving. What I have here is a slider that's representing how much of the vector field is allowed to take over the graph, basically. Okay? But you should be getting the idea of how this vector field is just one big swirl, right? It's definitely not conservative and has a definite curl to it. So make them a little smaller here. And let's just decrease the increment so that you get more of the actual vectors in there, in between. There we go. So this is what the vector field mostly looks like, right? Of course, I don't have the size all the way up to 100%. If I did have it up to 100%, like right here, you'd see you really have a difficult time distinguishing them from each other, which is why I have the slider here. This is truly the vector field, and if you do too many vectors, of course, as you can see, it's like trying to comb somebody's hair with a bald spot in the middle. It just you're never going to be able to make out what's going on anywhere else. So I have the slider with the size on it, so that we can get a good feel for the vector field shape. Right. So let's get it back to a comfortable point again. Let's say right there is pretty good. Now look, when I'm doing this vector field this way, you can see the tangent vector is going to always be pointing in this direction on the line right here. And at every single one of those points, the further out it goes, the dot product with these vectors gets larger, right? The direction increases, and then the actual size of these vectors right here are just increasing as they go outward like this. And then I turn around and go back along this curve. So the tangent vector is not always pointing in the same direction here. There's going to be a few points where it's parallel, sure, but over here it'll be a little shallower, and then when it gets close to the bottom of this curve, it'll get really steep in the other direction as well. So you're getting a lot of different contributions along this curve because of the way the vector field is swirling there. Okay, so that's why this would be a non-conservative field, the way these tangent vectors are interacting with those vectors. One last example of path independence on a simply connected region closed curve, right? So first, let's look at vector field capital A here. Y squared cosine x and 2y sine x, right? If I do the partial with respect to x of the second component, right? Derivative of sine x is cosine x. If I do the y derivative of the first component, right, the partial derivative with respect to y, is going to be 2y times cosine x. Same thing, right? So A is a conservative field. As soon as you realize that, you're going to be like, oh yeah, well that means A can be the gradient of some potential function. Great. So find the potential function. The partial of the potential function with respect to x has to be equal to the first component, and the partial of the potential function with respect to y has to be equal to the second component. If I do the antiderivative with respect to x, right? Antiderivative of cosine x is sine x times y squared. And again, if I do the y partial integral with respect to y, I'll get y squared sine x. Both of them give me the same thing, right? Remember, we don't need plus a constant in this particular case. So then I have my potential function here. Let's apply it now. I want to integrate on this vector field for a closed curve, again, like we did last time, the line y equals x from 0, 0 to 1, 1, and then the parabola y equals x squared coming back from 1, 1 to 0, 0. And I want to emphasize, and I want you to notice, it's the orientation of the two curves that matters here. I'm going from point A to point B, and then I'm using the other curve oriented in reverse to come back from point B back to point A. Okay, so the integral of C1 A dot dr plus integral over C2 A dot dr, right? The orientation is what matters here. Since this is a conservative field, I can use the fundamental theorem of line integrals here. That's just going to give me f of xy evaluated from 0, 0 to 1, 1. Notice the path was not, it didn't matter, right? The path didn't matter here because it's a conservative field. It's path independent. I'm just doing the antiderivative, right? Or the derivative of the, I'm doing the fundamental theorem, I mean. That's what I meant. Plus, again, this is a path independent line integral. So I can just go to this thing, but now it's being evaluated from 1, 1 back to 0, 0 because it's curved 2 and it's oriented that way, right? So I've got f of 1, 1 minus f of 0, 0. Okay? F of 1, 1 is sine of 1. F of 0, 0 is just 0. Plus f of 0, 0 minus f of 1, 1. Right? Top minus bottom again. So then I have plus 0 minus sine of 1, whatever that happens to be. And you'll notice the whole thing is 0. So therefore, the path integral, the line integral of A dot dr along the total path C, which is a path that starts at 0, 0 and comes back to 0, 0. That's what C is equal to 0. Because of two things. A is a conservative field, and C is a closed curve around a simple connected region. Okay? Well, I hope this helps you understand the fundamental theorem for line integrals. Stay tuned for Green's theorem. One last look here at some vector fields. We have this conservative field that we were just talking about with the same two pathways as the one before. And here's a small version. Of course, as you can see, I did the small percentage of the actual vectors that are there, but I have them pretty densely packed. Let's see what it looks like after. We'll get it a little bit bigger here. You can see it doesn't take long on this one. The sizes get out of control very, very fast. even to the point that I can't hardly pause it. So this is a pretty comfortable solid way. Let's see. Let's go. Well, no, that's too big. We'll stay here. You can see the vectors start really small in the center here, and then they spread out, right, as we go along this thing right here. They get bigger as we go out, and they have a definitive flow of a way out of this region. So they all flow into this center line here and here, and then they all get funneled basically into these things here and on their way out, right? There's no actual swirling going on here because anything that starts here is going to get pushed to here and pushed out that way here, and so on and so on. So right here in this spot, even though it's the vectors are really small, well, here we go. I'll just increase the size, and then let's focus in on just this region in here, if we can. Right? Let's increase, decrease the size just a bit to get a view there. Right? So you can see which way the vectors are pointing here. It's like they all want to lead into this line right here, but it has that same repetitive pattern there. And what's going to happen in this field is the way they spread out is it's just going to line up no matter which path you get. The sum of all of these different dot product directions are going to add up the same no matter which way you turn here. Right? Dot product here is going to give you all these dots, and then you'll get the same combination just in a different order basically, and then a different density possibly down in this region. But then they'll add up to be the same thing along the way because the vector field itself is conservative. Okay.